Mathématiques Bordeaux. You will talk to us about pairwise coprime integers in short intervals with polynomial growth.
Yep. Okay, thank you very much. So thanks to the organizers to give me this opportunity to join this very nice meeting to be in Phil's Institute and to join this very nice meeting in the honor of Ram. And I'm very happy, Ram, to wish you all the best for I have some experience of that, and you still have a few years at least, which are good for that. I want also to say I am going to present some old and some new results about the theme, and the recent one are joined with Henrik Ivanets, and Henrik unfortunately couldn't come. He's present with us here, but he doesn't want to speak right now. So he asked me also to give you his greetings on his behalf. So I am happy to do that. Okay. So, okay, let us start with the coprime integers. So coprime integers, essentially the question is to know, you take two, let us say random integers, and you ask what is the probability, with brackets, that they are coprime. So this probability is essentially means the limit of a frequency. You know, with integer, with something which is countable, making a probability, real probability space is not that easy. And density, for example, is very nice, but it is additive, but it's not sigma additive. This is the reason. But we think really of the density, that is to say we count up to some point n, we take the frequency and we look at the limit of this frequency when n tends to infinity. So essentially what you do, you take two integers up to n, and you count among those n square elements, how many are coprime. You divide by n, you tend to the limit, and you see what it is. And now it's something which is well known that the limit exists, and it is 1 over square root of 2, 1 over zeta of 2. And if you are using the tools which have been developed at the second part of the 19th century, it's just an exercise about Möbius function. It's not something very, very strong. A first-year student should know how to do that. So the first time it has been officially recorded, I think, was by Dirichlet in the, say, more or less the middle of the 19th century. But it's about sure that this was known, at least, or considered by Gauss and even Euler. So this is the starting point in some way from that. So maybe I write you the following. So you count the number of n up to capital N, such that, should take the pairs nm in 1n square, so that the GCD of nm is equal to 1. You divide by n, and you take the limit, and this tends to 1 over zeta of 2. Okay? N square? N square, yes, thank you very much. Okay. So this is the point. Now, the situation is also in the mid-50s, 1950s. There have been some, it has been introduced by possibly Watson was the first, but also then a few years later, Lambeck and Moser and Erdős and who was Lawrence, Erdős and Lawrence. And he studied the following thing, that you take a sequence f of n, a of n, let us say, and you are looking at the sequence, a of n is a given sequence of integers. You can't see it, sorry. A of n is a given sequence of integers, and you are looking at GCD of an is equal to 1, and then you are counting the number of n up to n, and the same thing, and then you are taking the limit. Does it has a limit? Does it tend to something? Okay, what is So this was just for one sequence, and then depending on the sequence, you had few results. So Watson started with a sequence which is integral part of alpha n, where alpha is an irrational number, and showed that the limit was 1 over zeta of 2. And Lambeck and Moser and then Erdős-Lorentz were studying something which was sequences of the type, you take f of n, which is a nice function, which is, you can, not f of n, f of t, f, let us say, is a function from 1 infinity to r plus. And what you are doing is you have a nice function with all the derivatives you wish, and to say that it has polynomial growth, which will mean that after some time there is one of the iterated differential derivative which will tend to 0. This is the way it means to be polynomial growth. And essentially, if you want to have some example, you can look at the function which is f of t is equal to t to the c, and to avoid something which is trivial, you take c, which is in 1 infinity minus n. When I refer to c, I will take something like that. So this function is a function which polynomial growth. Of course, you don't have integers, so what you are looking at is at the sequence which is integral part of f of n. Okay? So this sequence is called the Piateschi-Shapiro sequence. It has been introduced, as the name is saying, by Segal in 1930, and for studying the additive property of this sequence. And then Piateschi-Shapiro proved that if C is close enough to 1, then you have infinitely many primes in this sequence. Okay, so better to move to another thing. So there's one point that if you may be also interested in taking two different sequences. So, and I want just to show you that the problem is quite different, and the problem with n is much easier. Although, for example, what was proved if you take this Piateschi-Shapiro sequence, then it was only proved, this is curious, in about 2000, that for any C, you see what I mean by any C is any C satisfying this property always. For any C, then you have the following, that if you are taking you count the number of n up to n such that the GCD of n and n to the C is equal to 1. This is 1 over n. This tends to 1 over zeta of 2, as you may expect. So you have some independence, in some arithmetic independence, sort of arithmetic independence between the Piateschi-Shapiro sequence and the sequence of integers. Now I was mentioning taking two different things, two different sequences. So now you are looking at the following. Let an Bn be two integral sequences, integer sequences. Integer means natural integers. Be two integer sequences, and you want to count the number of n up to n such that, let us say, Bn an, the GCD is equal to 1. So how do you do that? You may detect the fact that the GCD is equal to 1 just by using Möbius function. So you will do the following. You are counting elements up to n, and then you want to say that the GCD of n and Bn is equal to 1. And so you just write the sum when D divides the GCD of Bn and An of mu of D. And this function, if you sum mu function over the divisors of an integer, you get exactly 1 if n is equal to 1 and 0 otherwise, because the Dirichlet series associated to mu is 1 over zeta. Just very classical. Now you can reverse as you would usually do. And then you have the following. This becomes the sum when D, well, D is something which I don't know exactly what it is, but D can be rather large because you have to consider all the divisors of this element. So it would be the maximum of the Bn and the minimum of the maximum of the An and Bn. Okay, so this can be rather large if you have a polynomial sequence which is large. So you have this, and then you will sum over the n, and so n is up to n, and you want to say that D divides both Bn and An. That is to say that you ask that An is congruent to 0 mod D, and Bn is congruent to 0 mod D. So this is the mu of D. You can factor it out, and then you count these numbers. Okay? So this is rather basic. And I want now to tell you the big difference if Bn is equal to n. So usually this is difficult because you have to know that An is both divisible, An and Bn are both divisible by D. And this may be quite tricky. And the big difference, if you assume that Bn is equal to n, for Bn is equal to n, then this is much easier. That is to say, for this sequence, like this one, because you have first, you know that D cannot be too large, since D is at most n, because you say that it has to be a divisor of some An, and An is at most capital N. So D is not too large. This is the first thing which is nice. And also the second thing which is nice is that you know very well what are the numbers Bn which are congruent to 0 mod D. This is just now summing n over n. So this is in this special case, what I'm writing here. N is up to n over D. And then you say that A of n over D, A of D times, let us put it M, D times M is congruent to 0 mod D of 1. So this is also much simpler. So for example, to quote some open problem, this is known that An and n and n to the c can be coprime for any c, and you have many of them and so on, and you have the right number. What about taking two consecutive elements? Let c be larger than 2, again with the condition that c is not an integer. C, do there exist infinitely many n such that, and I am starting to enter into the short sequences at the same time, so that the GCD of n to the c and n plus 1 to the c is equal to 1. Unknown. However, for a smaller c, if c is between 1 and 2, then we can say a few things about that. Okay? So this is okay if c is less than 2. So now we are also entering, we were taking 2 elements. So we can take also k elements. More than 2, this is, we enter into some generalization in some way. First generalization, so you take k elements, k sequences, if you wish, and look at f1 of n, blah, blah, blah. F is not a good notation. A1 of n, a k of n, and consider the question, how often is GCD of a 1 of n, blah, 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 all of them, a k of n is equal to 1. So if you take some random sequences, then what you would expect, the similar result that 1 over zeta of 2 will be just 1 over zeta of k. Okay? And this has been studied also. There is some extension of this result about n to the c. You can take n to the c1, n to the c2, and so on. And this has been studied by Bergelson and Richter about some 10 years ago, and showing that they are independent, and you have a limit which is 1 over zeta of k. What I want to talk about, if I still have a few minutes, is about pairwise coprimality. So pairwise coprimality, we are back to the beginning of the question, and you are considering the following. You take k, which is at least 2, and you are taking all the integers. So what you are looking at is, what is the density? Let us say the question is the following. What is the density of the set of integers n1 and k, such that, which are the density of integers which are pairwise coprime. So again, you construct a block of integers up to n. You take k of them independently, and you count the number of them which are pairwise coprime, and you try to see whether there is a limit and what can be the limit. And this was studied by Laszlo Toth in 1999, and he showed that there is a density, there is a limit density for the pairwise independent, pairwise coprime random integers, and he gave a formula for this density. Density exists and is equal, and he gave a formula for that. It is an Euler product. It is the product of a whole prime p of 1 minus 1 over p to the power k minus 1 times 1 plus k minus 1 over p. And you see that if you take p, k is equal to 2, you have product of 1 minus 1 over p times 1 plus 1 over p, and you have 1 over zeta of 2. Okay? No, it is by combinatorial. Yeah, combinatorial, and his proof is purely combinatorial. Yeah. But it's clever. I mean, it's a bit awesome, but it's fine. Okay? And so what, I still have a few minutes before coffee break. So we have been studying, maybe to give you some result about pairwise coprimality. So with Dormota and Müllner, in the Festschrift für Edward Wirsing recently, we showed the following, that if we take, let's see, in the interval 1, 2, if C is larger than 2, we know absolutely nothing about pairwise. Even 2 of them, we don't know anything. So there's nothing to help. But here we can prove the following. Then there exist infinitely many n for any k. There exist infinitely many n. Such that the sequence n to the n plus 1 to the c, let us say, blah, 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 n plus k to the c, k consecutive term in this sequence, then these are pairwise coprime. So that are pairwise coprime. Okay? So for the proof, we use indeed the machinery. No, okay, I have to stop about that. We use I don't write anything. The machinery of trigonometric sums and the Erdős-Turan, and so we try to locate. There is some combinatorial construction with these analytic tools, which permits to show essentially what we do is to prove that we can find infinitely many n's such that n plus h to the c. You see, if you use Taylor, you would say that first you have n to the c, then you have h times cn to the c minus 1, and then you have something which is a little o of n of a big O of n to the c minus 2. Okay, this is what Taylor's would tell you, and then you take the integral part, and if you are in good condition, you can find n such that indeed this is true, that and this does not exist any longer. And so you have something which is just linear, and then you can make some construction. But for this we need these tools. Indeed, we have given another proof recently, which is more general and doesn't use all this technology. This is why we can have many more functions, many more sequences, which is due to Sunil Naik and I. And we show the same thing when we replace n to the c by f of n with f of n, which has the following property: f double dash of n tends to 0 and is decreasing, and f prime of n tends to infinity when n tends to infinity. Sorry, you can't read. Yes, when C is bigger than 2, we don't even know whether there are two elements which are coprime. So even k is equal to 2 is not known. Yeah. And the point is really this, that in the Taylor expansion, you have one more term. So if you want to do something with GCD of 3 consecutive elements, then it's fine. But definitely there is really a difficulty here. This is one of the things I want to point out. Now we have been with Henrik Iwaniec, we have been looking recently as trying to find the density for those elements. Can we count them? And so in a work which is still in progress, we can, so I just announced this as work in progress, but I think it's rather safe. What we can prove is indeed find that there is a density for this number. So this is a good point, that we have a density. Essentially, what we have to do is, it is not written in this context, but it's something like that. It is first you bound this sum over D, And then you use Fourier analysis to get those conditions. And for that, you can treat many more functions than the Piatowski-Shapiro. In some way, Piatowski-Shapiro are just the archetype of what you can do. And we could find that there is a density. So in some way, I can announce it in it, that with Henrik, we have even this sequence as a density. Now, what is interesting, I will say a few words about the density and I'll stop. The density for, if you take, for example, for k is equal to 3, you have a certain product, let us call that AK, the value of a taut. Then if you take k is equal to 3, oh, let me go here. So A3, you know what it is, 1 minus 1 over p square, 1 plus 2 over p. This is about 0.28 something. Okay? Euler product is easy to find the approximate value as much as you wish. And what is interesting is that for this sequence, we have a different density. Positive density, let us say bk. And what we have for B3 is that B3, we can write it, we have some Euler product, or sum of two Euler products indeed, which is the product of the p of 1 minus 3 over p squared, plus 1/3 of the zeta square product. And this is about 0.3281, blah, blah, blah. So those numbers are not independent. And the fact that they are not independent is exactly carried by this formula. That in some way this and this are independent, but you have only 2 degrees of independence. And if you take 3 elements, then you get something which is no longer independent. And this is also connected to another work by Dormotat, Müllner, and Spiegelhofer and Shubin, where we look at the following. We take this sequence, Piatowski-Shapiro sequence, and we take all the elements and we reduce them mod p or d, whatever you wish, m. So you reduce them mod an integer, and you look at this sequence. So you have a sequence with finitely many possibilities for each number. And what you would expect is that if this sequence is completely random, then the number of blocks you have is something which is exponential in the length. But what we have is something which is polynomial in the length, what we could prove. So this is to appear in Israel Journal of Math. It has been accepted, but not yet appeared. Okay? And so there is some connection. Some way you have some memory of it, and you can do, okay, I stop here. It's time. Thank you very much.